In this video, I'm going to show you the Excel skills for section 8.3, which is doing a hypothesis test for paired data. So in our problem, we have 9 students took the SAT. Their scores are listed below. Later on, they took a test preparation course and retook the SAT. Their new scores are listed below. Test the claim that the test preparation had no effect on their scores. Assume that the samples are random and dependent and the populations are normally distributed. Use alpha equals 0.05. All right. So we're saying, our claim is that the course had no effect. So if you think about the scores, what does that mean if there's no effect? That means there's no change. So we're saying that if there's no change, if you subtract the two of them, if there's no change, that means they're the same number. There should not be a difference. So what we're claiming is that our average difference is 0. That's our claim. That if there's no change, that if you subtract them, there's not going to be a difference between them. So we're claiming that mu sub d is equal to 0. So the complement is that mu sub d is not equal to 0. So this is going to be a two-tailed test because we have the equal to, not equal to case. All right, so we need to set up our difference column. And you can do before minus after or after minus before. It really doesn't matter as long as you define what your difference is. Occasionally the problems will say set your difference to be such and such, in which case do it that way. But if it doesn't, then you can set d to be whatever you want. And so just for this problem, let's do d being after minus before. I'm just abbreviating it by a minus b, after minus before. So that means I'm doing my after minus my before. And if you had done it the opposite way, your numbers would have been off by a negative sign. If I get a positive, you'd get a negative and vice versa. And that's okay. It's correct. As long as you define how you're doing your difference, I will grade your problem based on how you do it. So if you did it the opposite way from the way I did it on my key, that's fine. As long as you set it up and I can see what you're doing, it'll still be completely correct. So please don't freak out and thinking you've got to set it up one particular way. You could have done this before minus after and come up with the exact same conclusion, and that would have been fine. But just for this one, I want to do after minus before. So we're doing the after minus before for our first data point, and then I'm going to drag that down. Since we did cell references, it's going to subtract each of them. So to find our average difference, or mu sub d, we need to average our differences. And then to find our sample standard deviation, or S sub d, we need to find the STDEV.S, the standard deviation for our sample of our differences. And then we see that we have a sample size of 9, so n is 9, so our degrees of freedom are 8. And I know I'm trying to squeeze all this in on one page, so I'm sorry if it's getting kind of small. All right, so I think we have everything that we need. So we're claiming that there's no difference, so the subtraction is 0. Since it's an equal to, not equal to case, it's going to be a two-tailed test. So to find our TC, we can do it by doing t dot inverse dot 2t of alpha, the area of those two tails together, which is 0.05. Technically, we split alpha up between the two tails. We had 0.025 in the bottom and 0.025 up top. And if you wanted, you could have done this as t dot inverse of 0.025, and you would have gotten the exact same thing, just looking at one tail versus the two tails together. But in this case, I'm going to use the t dot inverse dot 2t of alpha, so those two tails combined, and then our degrees of freedom is 8 to get our TC. And this is really plus or minus, since we have two tails. We have positive 2.306 up top and negative 2.306 on the bottom. And then to get our standardized test statistic, we plug into our formula. It's our difference minus, and actually I just realized I labeled this wrong. This should be d bar, not mu sub d. I'm sorry about that. So that's d bar. Because mu sub d is what we're claiming about. Wow. Blonde moment there. So our standardized test statistic, we have our d bar minus our assumed value for mu, which is 0, or mu sub d, divided by, parenthesis, S sub d, divided by the square root of our sample size, which is n. So our t is 2.401. All right, so that is above our critical value. If you visualize our bell curve, we have our negative 2.3 and our positive 2.3, our standardized test statistic 2.4 is bigger. So that means it's going to be way up high in the rejection region. So our decision is to reject H naught. So we say at alpha equaling to 0.05, there is enough evidence to reject the claim that the prep course had no effect. So it does appear that this SAT prep course improves students' grades. All right, let's do another one. So a weightlifting coach claims that weightlifters can increase their strength by taking a certain supplement. To test the theory, the coach randomly selects 9 athletes and gives them a strength test using a bench press. The results are listed below. 30 days later, after regular training using the supplement, they are tested again. The new results are listed below. Test the claim that the supplement is effective in increasing the athlete's strengths. Assume that the samples are random and dependent and the population is normally distributed. Use alpha equals 0.05. All right, so they do their bench press, they work out and take the supplement, and they have the after test. If we're claiming that this supplement is effective in increasing strength, that means alpha should be bigger. So if I set my difference up to be alpha, or after should be bigger. So if it's after minus before and alpha is bigger, this difference should be a positive number. So when we're setting up our hypothesis testing, all right, so we have our H and our H sub A. If it has an effect, it means our after is bigger. That means the difference after minus before is going to be greater than 0. So our mu sub D is going to be greater than 0. That's our claim. So our H naught is that mu sub D is less than or equal to 0. So again, because I set it up after minus before, that means if the after is bigger, it's going to be a positive number. So this difference should be positive. Should be after is bigger, so big minus little gives us a positive number, so that means our claim is that that difference is greater than 0. And it goes down in H sub A because there's not an equal to sign, so the H naught is the complement, mu sub D is less than or equal to 0. All right, so let's do our differences. We have after minus before, and again, you could have done it before minus after. The only thing that would be different is a lot of your numbers would have the opposite sign. If I have a positive, you'd have a negative and vice versa, and that's still correct. If you do it that way, you'll get full credit. I'm not picky about how you set it up as long as you show me how you're setting it up. All right, so I'm going to find all of my differences. Let's see if I can squeeze all this in here. I doubt I can. Actually, no, I can't. So I'm going to scroll down a little bit. We've read the problem. It's still up there. So to find our D bar, we average our differences. And then to find our S, we take the STDEV.S, our sample standard deviation of our differences. Our sample size N is 9. So our degrees of freedom are 8. All right, so this is a right-held test because H sub A is pointing to the right. To find our critical value, TC, we put all of our area in that right-held test. So we have 0.05 all the way up in the right side. That means the area to the left is 0.95. So we can do T dot inverse of 0.95 comma our degrees of freedom, which are 8, to get our TC. Then to get our standardized test statistic T, we plug into our formula. So we have equals D bar minus our assumed value for mu sub D is 0, divided by parenthesis S, divided by the square root of our sample size, which is 9. We get 2.17. So that number is bigger than our cutoff. It is going to be above it, which means we are in the rejection region. So our decision is to reject H naught. So we say at alpha equals 0.05. There is enough evidence. All right, so we're rejecting H naught, which means H naught is false. So that means H sub A is true, and that's where our claim is. So we've basically proven our claim is true. So we say there is enough evidence to support the claim that the supplement is effective in increasing strength. So we've just proven that whatever the supplement is, hopefully it's legal, does increase an athlete's strength.